Welcome y'all. Today we are going to see about the topic in electrical engineering, that is transmission and distribution. So transmission and distribution is a component of power system. It's an important component in power system. Transmission and distribution. Transmission of power and also distribution of power. It is consisting of the various transmission equipments which are transmitting the power, mainly essential for transmitting the power, and also distributors, various type of distributors according to the type of voltages used, according to the load connected to the system, different type of distribution system also. So as a whole, what is power system? In this slide, what is power system? You can see the total view about the power system. So power system consisting of starting from generating station. The generation may be various kind of generation. It may be a thermal power generation, atomic power generation, or maybe a solar power generation, wind power generation, such a renewable energy source also will have different type of power generating stations. So it may be a generation of AC as well as a DC. Generally, 90% of the generation of power is AC. In solar only we have the power generation in the form of DC. So different generating stations. Different generating station, they are generating the electrical power with a different type of voltages. Generally we are generating the AC generating power in the 11 kV voltages. So we have 11 kV voltage generation. The next component is transmission, that is primary transmission. Primary transmission. In the transmission, we are going to step up the voltage levels. We are having such advantages in stepping up the voltages. So stepping up the voltages only, we have some benefits. We can reduce the amount of current, and also for long distances, increasing the voltages will be a useful one for transmitting the power for a very long distances. We have to increase the voltages. So using different transformers, step up transformers, we can step up the voltages. So up to 220 kV. So nowadays we can step up the voltage up to 700 kV also. So here the voltage is stepped up from 11 kV to 220 kV. So primary transmission. So it is a transmission of power through various transfer lines supported by a long towers. Different lines are supported by long towers, steel towers. So it is the primary transmission. The secondary transmission. So what are all about above and after the primary transmission is stepping down of the voltages. Whether it is a secondary transmission or primary distribution or secondary distribution, here we are stepping down the voltages. So stepped up voltages up to 220 kV here, it is being stepped down. So 220 kV or 33 kV. So here the voltages, the high voltages 220 kV is being stepped down to 33 kV, step down. So the next one is receiving station 2. Receiving station 2. So we have different type of substations. So from the 33 kV, we have a 33 kV of substation, from which we can distribute the power to various loads, the feeder lines. Substation 2, here also using step down, further stepping down the voltages from 33 kV to 6.6 kV. Here the voltage is stepped down further up to 6.6 kV through various feeder lines. So next to that, we have distribution transformer. Using transformers, we have furthermore stepping down from 6.6 kV to 230 or 400 voltage. If it is single phase, it is 230. If it is a three phase, it is 400 voltage. And connected to the various service lines. The distributors are connected to various service lines according to the loads. light loads or industrial loads, we can distribute the power through these distributors. So again, in the primary transmitter itself, we can step down. Suppose the industries of very high voltages, using very high voltages, directly we can step down the voltages and use that voltages for their industries. So here 220 kV to 33 kV. That's using step down transformers, the 220 kV is stepped down to 33 kV transformers, using which we can supply very bulk load customers, factories and industries up to 6.6 kV. So directly we can get the power from primary transmission itself, using which we can feed the loads of bulk load consumers, factories and industries. So with this, we have a clear picture about transmission and distribution. What are the various generating stations? What are the transformers involved? Various components in transmission and distributions. In transmission, we have transformers, the supporting towers made up of steel, and also poles of wooden and steel type. The transmission lines, the main part of the transmission. So it is being made up of aluminum and copper conductors, being insulated. So copper and aluminum conductors. The various these different distributors according to the type of the loads and the distance up to which we have to distribute the power. So based on that, according to our easiness, so we can have different type of distributors and feeder lines. So totally this picture is telling about the various components and also type of transmission and distribution. So generating station, the voltage is about 11 kV. It is being stepped up to 220 kV using step-up transformers. Then primary transmission, the high voltage transmission. The receiving station is, we can further step down up to 220 kV. From 220 kV up to 33 kV, we can step down. Then we have secondary transmission. So through which we can further step down the voltage up to 33. The 33 kV is further step down in distribution, primary distribution. So from substation, we can step down the voltage from 33 kV to 6.6 kV. So directly we can take the power from this 6.6 kV to large bulk loads like factories and industries. The secondary distribution is the distribution for consumers and service lines. About the voltages of 230 voltage and 400 voltage. Whether it is a single phase, it is 230. If it is a three phase, it is 400 voltage. So based on which we have the secondary distribution. It is a line diagram of a typical transmission and distribution scheme. So we have the primary transmission, secondary transmission, primary and secondary distribution. So that we have seen in the one line diagram as well as the clear picture of the TAV. And various components of distributions. As we already know, it is substation. So what is substation? That is consisting of transmission lines bring the power up to substation at a voltage level of 22 or 33. At the substation, the level is reduced to 3.3 kV and 6.6 kV. So substation is a station where we are stepping down the voltages. The voltages are 33 kV into 3.3 kV or 6.6 kV. In such a way, we are stepping down the voltages. So this is a place where we are stepping down the voltages using transformers up to 3.3 kV and 6.6 kV. Then what is local distribution system? So it consists of transformer. Here also we have the stepping down transformers. They are stepping down the voltage level from 3.3, 6.6 to 400 voltage and 230 voltage. So from the kV level to normal voltage level, here we have the voltages being stepped down. It is also called distribution substation. So substation, distribution substation, then feeders. In distribution, the next main component is feeders. They are all conductors which are of long conducting capacity. The feeders connect the substation to the area where power is to be finally distributed to the consumers. So feeders are connecting the loads and substation. So no tappings are taken from the feeders, so that they are directly connected to the loads. The feeder current always remains constant. Here the current is being maintained at a constant level. The voltage drop along the feeder is compensated by compounding the generators. So voltage drop. So we have voltage drop in the lines that may be compensated by the compensation. Compensation means compensation of reactive power. Using that reactive power compensation device, we can compensate the reactive power, using which we can make up the voltage drop we faced. So here the reactive power compensation device is a compounding generators. Compounding generators using synchronous generators, we can compensate the reactive power such that balancing the voltage drop. Next component is distributors. These are the conductors. They are also conductors used to transfer power from distribution center to the consumers. From the distributors, the tappings are taken for the supply to the consumers. So there is no tapping in the feeders, but here we have the tappings using which we can tap the power to the consumers. The voltage drop along the distributors is the main criterion to design the distributors. Here also we have the voltage drop. Service mains. These are all small cables between the distributors and the actual consumer premises. So what are all the conductors coming to our home? When we are regularly seeing that conductors, they are called service mains. So consisting of the energy meters, whatever the power we are consuming. So everything we have in the service mains. The interconnection of feeders, distributors and service mains. The connection between substation, feeders, distributors and service mains. It is clearly depicting the distribution of power from substation to the loads. There is no tapping on the feeders. Here the feeders are no tapping from the feeders. From the feeders we are not taking any power. But PQ, QR, RS and PS are the distributors which are supplied by the feeders. No consumer is directly connected to the feeder. The service mains are connected to the supply to the consumers from distributors. Tappings are taken from the distributors. So from the service mains we are having the tappings. Then in the transmission we are stepping down the voltages. So what is the advantage of stepping down the voltages? So we have stepping down of voltages only in the primary transmission. So what are the advantages by stepping up the voltages? Summarizing the above discussion, the advantages are the line losses are inversely proportional to the square of the voltage and power factor. So line losses are less. So being stepping up the voltage is being increased. But the line losses are inversely proportional to the square of the voltage. So how much we are increasing the voltage, proportionally we are minimizing the line losses. The line losses taking place in the lines. So that is the one reason. So line losses are minimized here. For constant losses, the volume of copper required is inversely proportional to the square of the voltage and power factor. If the copper required is much less for high voltage transmission. So that here the requirement of copper is also decreased. By increasing the voltage, we can minimize the requirement of copper. For constant current density, the line efficiency is very high for high voltage transmission. So by increasing the voltages, we can maintain the current density as a constant. So this line, so that we have line efficiency, very high line efficiency. The percentage line drop is very small for the high voltage transmission. Line drop. So by increasing the voltage, normally we are decreasing the current. So the line voltage drops and also the losses are being reduced here. It may be noted that along with the voltage level, the power factor also plays an important role. Higher power factor also gives less losses. So by using high voltages, we can improve the power factor, reduce volume of copper and increase line efficiency. Hence, consumers are always recommended to maintain high power factor values. So in this case, we have advantages on high voltage transmission. Then what are the disadvantages? Higher the transmission voltage, higher is the insulation required. So being increasing the voltage, we have the requirement of insulation is increased, which can cause problems in connection with conductor supports and clearance between the conductors. This is the main disadvantage. By increasing the voltage, we have insulation problems. Between the conductor supports, we need more insulation and also the clearance. It is also affected by increasing the voltages. Higher insulation means high cost. In the insulation also we have increased cost. The cost of transformers, switchgear and other equipment is also high for high voltages. Based on the voltages, we have to increase the cost for transformers, switchgear and other equipments. Higher the voltage, severe is the corona effect. So corona effect is the effect taking place surrounding the conductor. The noise produced and the light and loss, light and AC noise, using which there is a power loss surrounding the conductor. It is due to the ionization of the air surrounding the conductor. So using which we have much amount of power loss. By increasing the voltage, we have increased power effect. So these are all the, we can say, disadvantages of high voltage. The practical transmission and distribution voltage levels for generation, we have 6.6 kV, 11 kV, 22 kV and 33 kV. For primary transmission, it's a regular practice we are using in our India. We are using this regular practice. So generation voltage is from 6.6 kV to 11 kV, 22 kV or 33 kV. Then primary distribution, the next stage after generation. Here the voltage levels are 66 kV or 132 kV or 220 kV or up to 400 kV. These are all the voltage levels normally practiced in primary transmission. In secondary transmission, so here using transformers, we are stepping down the voltages. So again we have the voltages of 11 or 22 or 33 kV are all the voltages in secondary transmission. Then primary distribution. Here also the furthermore stepping down of voltages. So here the voltages are about 6.6 kV or 11 kV. In secondary distribution, further stepping down the voltages. It is about 230 kV or 400 voltage. So normally we can say 230 voltage is a single phase voltage, 400 voltage is a three phase voltage. Then types of transmission. So two types of transmission. It is overhead and underground system. So overhead lines we can transmit the power. Similarly, we have underground transmission also. Comparing the underground and overhead system of transmission. So in various ways we can compare the underground and overhead systems. So overhead system is so through by the support of towers, poles and very strong supporting means we are transmitting the power. But underground systems, so no need of such type of supporting system. So only the conductors are protected by using various surmounted materials. But in our transition, we have different type of supporting system needed. So in this way, we can classify underground and overhead system. Underground system transmission is by using the cables. Only through the cables we can transmit the power. But in overhead system, we can use lines. So lines made up of the conductors like copper and aluminum. Next, second one, all the cables must be properly insulated from each other. So the insulation is very essential in underground systems. The cable must be insulated. But here the appropriate spacing between the conductors such as insulation. No external insulation is necessary. Here there is no external insulation. But between two conductors that may be affected by wind, the external and the environment. So from which we have to protect the conductors. In that way we need insulation. In underground system, the insulation cost is very high. So in all the way we are using insulators. So the cost is very high. No insulation cost as the air acts as insulator. So here we are replacing the insulating property of the air also. So no insulation cost, no additional insulation cost. Transmission over long distances is not possible as laying of cable is difficult, costly and complicated. So for long distance, it's not possible in underground system. So only for a particular area of particular length, for a particular distance only we can provide this underground. But in overhead system, overhead transmission system, the distance for very long distance we can transmit the power. In underground system, the voltage level used is 66 kV, but up to 400 kV we can transmit the power in overhead. The maintenance cost is less. So once it is invested, there is no further more cost to be spent for underground. But in the overhead system, we have a continuous maintenance cost. Maintenance. The faults due to lightning, short circuit, storms, etc. are eliminated. So no environmental effect in underground cable system. But here in overhead system, we have the effect of the environment and also the natural phenomena. It is very safe due to insulation used. So the safety cost we can have underground system is being better than overhead. But here the conductors are bad without insulation means dangerous. The conductors are very bad, not insulated. So that only we have the dangers of the damaging of body of birds sitting on any two conductors. Any two conductors, there will be a short circuit. So it is very dangerous. Maximum stress is on insulation between the conductors. The stress on insulation is very high in underground. Maximum stress is between conductor and earth. So only stress is between conductor and earth only. The beauty of the area towns is well maintained. So the complexities and the congestion is being reduced here in underground. Congestion. But in overhead system, it is affecting the system and also making some effect through the communication lines and also through the trees. So it is easily to be affected by the environment. The size of the cable is high, the size of the conductor is less. The voltage drop is less in underground system, but here the voltage drop is more. So in this way, we can classify, we can compare underground cable system and overhead conductor system. Then EHV AC transmission. This is a type of transmission system. AC transmission. EHV AC. Abbreviated as EHV AC. The expansion is extra high voltage AC transmission. Extra high voltage AC transmission. In recent years, gravity energy is generated and consumed at a very high rate throughout the world. There are many new trends and developments which have occurred in the field of transmission of electric power, which leads to use high voltages extensively. So for use of that high voltages, we are going for this EHV AC transmission. This is a AC transmission, AC high voltage transmission. So using which we can step up the voltage up to 765 kV using various kind of voltage transformers. Configuration of EHV transmission. So how they are configured. So initially we have the generating station, two circuit breakers. It is connected to bus bar at substation. So bus bar is the meeting point of various lines. So in between the substation, we have intermediate substation for reactive power support. So reactive power support is if we have any voltage drop or any voltage increment. So using the reactive power support, we can regulate the voltage. So that provision is made in the substation. So here is a configuration of very long UHV or UHV three-phase AC transmission. High voltage direct current transmission. It is also high voltage transmission, but in the form of DC. Like extra high voltage AC, here we have HVDC, the DC high voltage transmission. In early days, the transmission, distribution, and utilization of electric energy was dominated by AC. After the introduction of large, high-powered mercury or rectifiers, so the invention of rectifiers, DC, considered for transmission. So inclusion of this, we are going for HVDC transmission. So what are the advantages? We have some advantages over EHV AC transmission. So wherever we cannot use the EHV AC transmission, we can go for HVDC as a substitute. Principle of HVDC transfer system. So using this picture, we can get some idea about the principle of HVDC transmission. So AC system. So normally we have the AC generation. 90% of generation is from AC. So actually, even though it is HVDC, it is connected to the AC system. So using AC systems, AC system, we are stepping down the voltages using transformers. Stepping down. So in the AC system, we are stepping down the voltages. In the AC form, we are processing HVDC system. So HVDC system is consisting of rectifier station and inverter station. In between we have rectifier and inverter station. So why this rectification and inversion? So rectifier is a converter, power electronic converter, using which we can convert the AC into DC. And also we can make some controlling arrangements in the form of voltage or current flowing. And also the other end is inverter station. So here also we have power electronic device, that is inverter. So which is used to the control DC into control AC. Because this AC is to be connected to the further AC systems. So using HVDC system, we can interconnect different AC systems. HVDC system is in between any two AC systems, using which we can interconnect many AC systems, using which we can provide a controlled DC power transmission in the parameter of voltage, currents, power, frequency, not frequency, in the form of voltage and current in a controlled manner. We can use this HVDC system as an alternate for the HVAC. Advantages of HVDC transmission. So here we are using only two conductors. So requirement of conductors is very much reduced. There is no stability problems with these systems. So there is no stability problems. It is a in the AC system we have the problems of frequency, but here no such kind of frequency problems. So no stability problem. The line length is not limitation as there is no charging current in DC systems. So here there is no charging current. Being in DC, there is no charging current. Therefore, no losses, no further losses. Due to charging current, there is no losses. Greater power transmission per conductor is possible with DC. So power transfer per conductor is very high in DC. There are no serious problems of voltage regulation as there is no reactance knob that exists in DC at steady state. So no serious problems of voltage regulation. The corona loss is low in DC systems. The radial interference with the HVDC is less. Therefore, no corona produced surrounding the conductors. The losses are less in transmission. The fault level increases with interconnections of AC grids through AC lines, whereas interconnection of AC grids through DC lines does not increase fault level to that extent. So we have no greater fault level complications in DC compared with the AC system. With the HVDC link, there is easy reversibility and controllability of power flow. So you can easily control the reverse power from AC to DC or DC to AC using the converters and rectifiers and also by inverters. We can make reversibility of the power. Shunt compensation is not required in DC lines, but it is very essential in AC system. Shunt compensation for reactive power. Intermediate substations are not required with HVDC. There is no stepping down of voltages. We need substations in AC systems, but that is not needed in HVDC transmission. During fault with HVDC, the grid control of converter reduces the fault current significantly. So during fault time, using converter, we can easily reduce the fault current. But that is not possible in AC systems. We have to use the circuit breakers in that situation. Next one, the transient stability of the power system can be improved by making parallel connection of HVAC and HVDC lines. So we can use HVAC and HVDC lines because here we have interconnection of AC as well as DC. So using these two, we can make the transient stability as a stabilized one or enhanced one. Then what are the disadvantages? The power transfer with the HVDC is not economical if length of transfer is less than 500 kilometer. So the only advantage of HVDC in distance wise is after that is above 500 kilometer. Above 500 kilometer only we have economical situation. But below 500 kilometer, the number of lines used in many cases it is economical. The AC is the only economical below 500 kilometer. Actually, DC system is economical only after 500 kilometer of the line length. With the multi-terminal DC, the circuit breaking is difficult and expensive. There are multi-terminal DC, so we have inverter and converter station. So circuit breaking is difficult and also expensive. Considerable reactive power is required by converter station. The converter stations are requiring reactive power. So they are being used in many power running devices. We have the reactive power common seeding device and converter stations. Harmonics are generated with the DC system. So even though we have low frequency problems in DC system, with the intention of the intervention of the rectifiers and inverters, they are all normally power run devices. So the production of harmonics also increased here. Overall capacity of HVDC converters is low. Loading capacity is low in terms of HVDC converter. There should be local supply of reactive power if required. If required as HVDC will not transmit reactive power. There is no transmission of reactive power. Like EHV, VC, here there is no transmission of reactive power. So we need a local supply of reactive power. Whenever and wherever we need, we have to locally supply the reactive power for the reactive power compensation in order to maintain the voltage. The maintenance of insulators in HVDC system is more. The cost involved in maintenance of insulator is very high in HVDC system. So in these ways, HVDC transmission is some disadvantages too. Types of HVDC systems. So depending upon the number of conductors used, and number of components, the inverters and the rectifiers used, we can classify the HVDC system into three types. So first one is monopolar, bipolar, and homopolar. So in monopolar, in the figure 1.22, we have the monopolar HVDC transmission system. So it is only one pole. So here we have only one pole conductor, and the return path is provided by the permanent earth or sea. So through sea also we can use this monopolar system. So we have only one conductor. The earth is acted as the second conductor for the return of power. The pole generally has negative polarity with respect to earth. So the pole used, only one pole used here is negative with respect to earth. So here we have two stations, the converter and inverter station. They are connected by only one pole. The return path is through earth. Bipolar HVDC transmission. So here we have two poles. Bipolar means two. So here we have two poles. One is positive and another one is negative with respect to earth. So here the power is transmitted between the two poles, the positive and negative polarity poles. The power is being transmitted through the converter and inverters. So it is used for very long distance. For very long distance case, we can use this bipolar system. The midpoints of converters at each terminal are earthed through electrode and earth electrode. Earthing is made by this. Power rating of one pole is about half of bipolar power rating. So one pole is of half power rating of the total power rating. The earth carries only small out of balance current during normal operation. So with the connection is the closed circuit is between the positive and negative polarity. There is only a small amount of current only flowing through the earth as a leakage current. The normal bipolar HV system consists of two separate monopolar systems with a common earth. So in bipolar we have two separate monopolar with a common earth. The two poles can operate independently. Normally they are operated with equal currents and hence ground carries no current. So whenever they are operated at same current, same current reading level, there is no current through the earth. So it's a bipolar system. So instead of one set of converter and emitter, here we have two set of converter and inverter in between the two AC systems. Homopolar HVDC. The system consists of two poles. Here also we have two poles, but they are all in same polarity. And the return is through the permanent earth. So two poles, but the return is through the earth. So same polarity, two poles. Two poles are interconnected. The return path is earth here. So it is homopolar. Next, the fourth one is back-to-back HVDC coupling system. There are two HVDC coupled. In this system, there is no DC transmission line, but the rectification and inversion is in the same substation. So there is no line of transmission, but only we have the conversion and inversion. So that is being taken here, back-to-back HVDC coupling system. And also we can make control over in the form of DC itself here. So that control is being only done here. No transmission of power or only controlling. Electrical layout diagram of typical 230 kV and 110 kV substation. So it's a structure of the substations. Here we have different lines, transformers, the bus arrangement of different voltages, transfer bus, main bus like that. So how they are interconnected in substation, that is clearly depicted here using one-line diagram. Substation one-line diagram. A typical pole mounted 11 kV power, 400 voltage substation layout. So how it is stepped down from 11 kV to 400 voltage. So through transformer and using various switchgear operations in this substation. So next we have the insulators. So insulators, they are mainly using two types of this transmission and distribution. Whether it is a AC transmission or DC transmission, we have insulators. So what are all the insulators using transmission and distribution? Different type of insulators using transmission and distribution. So types of insulators according to the usage and its own advantages, we can classify the insulators into five types: pin type insulators, suspension type, strain insulators, cycle insulators, and stay insulators. So the overhead lines, what are all the insulators? Pin type, suspension, and strain type. Normally pin type, suspension, and strain. So pictorially, you can clearly get idea about the pin type insulators. It is the pin type insulators. So insulators. So get a voltage level. So for a voltage level of 11 kV, we can use this pin type insulators. Whenever the voltage is increased, so up to 33 kV, 43 kV, and 66 kV, the pieces, number of pieces are increased. So it is a one piece structure. The piece, by increasing the number of pieces, we can use these pin type insulators according to the increased voltage levels. So pin type insulators, structure of the pin type insulators with conductor. The post insulator having cement threads which are lined with a soft material like lead. The pin is screwed into such a cement screw. So for the provision of the conductor through the insulators. Next one, suspension type insulators. It is being suspended from the pole. In that way, it is named as suspension type insulators. As the voltage level increases, pin type insulators become very bulky. So by increasing the number of pieces, so it is looking the bulky one. So at that time, comparing the cost also, so we can go for alternative. that is suspension type insulators. The most popular insulators used for very high voltage lines are suspension type. So mostly we are using these suspension type insulators. These insulators have a number of porcelain discs. Here the number of porcelain discs insulators are in the form of disc. These units are connected to one another in series with the help of metal links. Using metal links, we have different discs connected together. This forms a string of porcelain discs. The topmost insulator unit is connected to the cross arm. The topmost is connected to the conductor, cross arm of the tower, while the lowest insulator is made to hold the conductor along the conductor shoe. Each unit is designed for a low voltage for say 11 kV, but a string of such units give us the proper insulation against very high voltage levels. So each disc is capable of insulating a voltage level up to 11 kV. By increasing the number of discs, so we can increase the voltage levels. Two main types of the suspension are cemented cap and avalanche or interlinking type suspension type insulators. The suspended distance or the distance between two sequent discs. P-type insulator, TVS P-type insulator. Suspension type insulators with 3 units. Here we have 3 discs. The topmost disc is connected to the tower, and the lowermost is connected to the line connector. So between tower and conductor we have this insulation. Advantages of suspension. For higher voltages, these are cheaper. For very high voltages, this is cheaper than the pin insulators. Each unit is designed for a low voltage level such as 11 kV. But by connecting such units in series to form a string, insulator for any higher voltage level can be designed. For any voltages, for any increased 11 multiplied voltages, we can use this suspension type. In case of failure of any of these units, the replacement would can be done very easily. So using this, we can any replacement immediately. The line voltage is required to be increased at some later stage to satisfy the increased load demand. Then just by adding additional units to this string, same insulator can be used. Adding such units is very easy. So whenever we need additional string, we can easily add some strings to this system, suspension system. This type of insulator provides greater flexibility to the line. The string is suspended and is free to swing in any direction. So it takes the cushion so that mechanical stresses on the line are minimum. So they are holding the stresses produced on the conductors. So by moving on any way, they are stress reliever. They are acting as stress reliever, which is to be affected the conductors. So stress on the conductor is withstood by these suspended insulators. When used with the steel towers, the line conductors are less affected by lightning. This is because the conductor is lower than the earth's cross arm and the arrangement acts as a lightning arrestor. So as a lightning arrestor arrangement also, the suspension insulators are used. So comparison of pin and suspension type. Normally the suspended type. So compared with the pin, how it is efficient. Pin is costlier, but for higher voltages, they are cheaper. Suspension type are cheaper. Pin type are only voltage levels up to 33 kV. But here each disc is designed for 11 kV. So using this number, by increasing the number of discs, we can go for very high voltages than the 33 kV pin type. For higher voltages, these are bulky and heavy. The pin type are very bulky and heavy. But in suspension type, the voltages for higher voltages, the string is not bulky. So only we are adding the number of discs. The replacement is difficult here, but it is very easy in suspension. Binding wire is used to hold the conductor. To hold the conductor, we have further requirement of the binding wire. So no such wire is not used in suspension. It is not required. At later stage, unit cannot be modified. There is no modification of units to be connected, but here it is possible. It is not suspended, but is fixed. But it is being suspended. It is the mechanical stress is easily relieved here. Chances of getting affected by lightning are more in pin type, but it is less affected by lightning. Then strain insulators. Strain insulators, they are horizontally fixed with the connectors. The insulators are used where there is dead end of the line or corner line is and a shock curve on the line is crossing the river is. So in that specific situation, particular situations, we are using the strain insulators. Shackle insulators. So these are also called spool insulators. These are primarily used for low voltage distribution. For low voltage distribution, normally on secondary distribution, we can use this type of insulators. Stay insulators. That is also called egg insulators. In case of low voltage lines, it is necessary that the strays are to be insulated at a height of not less than 3 meters. So in that cases, we can use these stay insulators. So different type of insulators we already studied. The main requirements of insulating material used for cable, that is in underground transmission. The requirement of insulation is high insulation resistance. The resistance should be highly insulated. High dielectric strength. The high dielectric strength should be increased. And also good mechanical supports. They should not be affected by chemicals. They should not be non-hygroscopic. So with this consideration only we can design the insulators for underground distribution. Comparison of underground cables and overhead lines. So comparing the cables and the lines here. So already we have seen the comparison of cables and lines based upon the efficiency, voltage levels. So we can have where it is to be used. In that way we can compare underground cables and overhead lines. So comparison between cables and lines. So with this, let us wind up our session. So here we have studied about the basic phenomena of transfer and distribution, and mainly the insulators, supporting component insulators, different type of insulators, how they are used in overhead transfer and underground cables. So with this, let us wind up our session. Thank you.